Chapter Lab 11, Meldes Experiment, which you can find on the handout on Lab 11. It's called Meldes. It's an experiment for looking at standing waves on a vibrating string. And this is the setup that we'll be using for this. It consists of a pulley and one end, and on the other end of the pulley we have a weight that's hanging from it of varying size, dimension, varying mass, depending on what type of modes we're trying to get, and I'll explain this in a bit. So we hang this over the edge, so it gives us what we call produces a tension in the spring. In the string, I should say. And then the string is 1.5 meters from this point with this vibrator. And the way they make this work is we have a vibrator that goes with the AC current of 60 times a second. Now, as you see, that this generates a frequency of 120 hertz. So we have this, and what we're going to do, I'll explain the theory a little bit, is calculate what the tension should be for various what we call standing wave modes. So this is part of chapter 11 as far as that's concerned, and we'll get into that. So I'm going to explain a little bit about the theory, and what we're going to be looking at is, again, this will be part of chapter 11, but what we're going to see is we talk later on, later part of the chapter, we can generate waves, and chapter 11 talks about standing waves. So look at the lecture for chapter 11, perhaps before you do the lab, because 10 and 11 will be the basis of the next test. And standing waves are resonance, and for this part, we're going to be doing standing waves on a string. For lab 12, we'll be doing standing waves in air. So that'll be the basis of lab chapter 12 for the final test. So a vibrating string or wave, if we have it just the right frequency, we can generate a standing wave. All right, this can be on a string, it can be for a piano, an instrument. And if you look on the video link for the Tacoma Narrows disaster, they talk about resonance there when you don't want it to occur. So what we're going to have is generate what we call standing wave, because for the right conditions we can get a nice wave going up and down on there. All right, so for this lab, as you have the handout, and I just showed you what the setup looks like, is we have the hanging mass on one end of the pulley. So this is M. There's a frequency of 120 hertz, which is 2 times the frequency of that. And for the right conditions, we'll get a standing wave that goes up and down perfectly. All right, so how do we calculate that? I'm not going to get into the theory of it too much, but it depends on a couple things. It depends on the frequency, depends on the length of it, it depends on the mass per unit length of the string. So we'll be doing this for 2 different cases. One case where we have a thick string, another case where we do it for thin string. And I'll explain that as far as calculating for the thick string, and then all the calculations will be similar for that. So how do we do this? So it depends on the mass per unit length of the string, the length of the string that's vibrating, the frequency, g, acceleration of gravity, which is 9.8 meters per second squared, and then it'll generate different what we call modes, depending on which one, how much mass we have there, the right mass. So we're going to be looking on data table table 1 on the thick string, we'll be looking for different modes going from 9, 8, 7, 6, 5, because as we see, as the modes, as this gets smaller, this gets larger. So I'll do an example of this. We have a thick string which has a mu of 0.001565 kilograms per meter squared, and a thin string of 0.000175. So this approximately weighs 8 times the thin string. So I'm going to go through one calculation here, and I'll do it for the thick string, and then I'll show you how to calculate it for the thin string, every one without redoing it each time. So here is the formula for calculating the mass that will create the right tension to create a standing wave, and then we'll actually verify it with each of the different cases. So to do this for the thick string, right, so what it's going to be is 4 times this number, 0.001565, times the length of the string that I set this at, 1.5 meters times 120, divided by 9.8, and for the example, I'll use 8, and for n equals 8, we end up with 0.323 kilograms, or 323 grams for n equals 8. All right, now you can calculate for each one, because for the lab, we're actually going to be doing it for 9, 8, 7, 6, 5. So to calculate this predicted hanging mass for any particular one, fill out this table by doing 20,696 divided by n squared, which would be 9,876. So and it would be 9, 8, 7, 6, and 5. So you calculated that for the 5 data results we're going to do. Enter that in column 1. That'll be the mass in grams. You can do it in kilograms or grams. The table shows kilograms, but since the masses will actually be hanging from our units of grams, this will be in grams. All right. So you can complete data table, the second column, using this formula, and get that. All right. There'll be some questions related to that. All right. Next thing I'm going to do is calculate it for the thin string. Right, so in this case, so you calculate that, so data table 2 will be calculated for the thin string, and in that case, we have, this is the mass, and I'll show you when we actually do the experiment for each part. So this would be 0.000175, and I'll do it, because in this case, however, instead of 98765, we're going from n equals 6, 5, 4, 3, 2, and so we'll pick the first one, n equals 6, and I will calculate that for you. So, this is what we had before. This is what we have now. So I'll calculate this. All right, so we get 0.5. 8. And this will be equal to 2,314 divided by n squared, and for n equals 6, m would be 0.0643 kilograms, or 64.3 grams. So you would calculate this again for data table 2 in the predicted column, all the way down for n equals 6, n equals 5, n equals 4, n equals 3, and n equals 2. And we do it just based on, it works better trying to do the actual experiment with picking these particular numbers. So I will go through this. So you calculate the data table, again, 2314 divided by n squared, which in this case is 6. And that's it. So that's the first part, setting up the data table. We'll next measure. There's a vibrator. Here's our length of string of 101.5 meters. We have the mass hanging on the end. And after you've done the calculations, so I know approximately are, and you can look at, if you've done them right, you'll get a nice, it should be reasonably close to what I'm going to measure. So what I'm going to do is use these calculations. So I'm going to start with 200 grams, because I know it's approximately close to that. And what we'll see, it'll be kind of hard to see, but there's nothing right there. So I'm going to add 50. And then I know approximately what it should be. I'll do 255. That's getting pretty close. You can maybe see the individual notes. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 antinodes. So let's try doing. Seems to be about perfect right there, at about 255. So we have 9 antinodes. I'll write this down. So for n equals 9, we get 255 grams. Okay. Next I'm going to do is try and do n equals 8. Right? So with 9 we had 9 antinodes, 8 nodes. So I'm going to add some more weight to it. So we had 250. Right? Add another 50 will give me 300, add 20, pretty close. Let's try a little bit, it's not quite there. Ooh, very nice. Okay, we have now at 322. So we have 8 antinodes, 1, 2, 3, 4, 5, 6, 7, 8. So for n equals 8, 322 grams. Okay. Next I'm going to do n equals 7. Okay. Back down to 300. Add 50, that gives me 350. Need another 50 here somewhere. That's okay. $50. All right. 350 add 60 gives me 410. Okay, it's coming there. We add 5. N equals 7. You can see 1, 2, 3, 4, 5, 6, 7 antinodes. So for N equals 7, I have 422 grams. Next I'll do N equals 8. N equals 6, I should say, so we'll take all these weights off. Okay. And I'm going to start, I'll add 500, so I have 550. And then, let's see, I'll add 20. That's 570. Ooh, we're really close. And I'll add, let's add 5. Go down the other way. $74. 572. 572. So we got 1, 2, 3, 4, 5, 6. N equals 6. 572 is our answer. Okay. And finally, we're going to do, try and look for n equals 5. Okay. So we're back to 550. 600. Okay. 700. 800. 820. Oh, that'll do it. Oh, that's wonderful. 827. We got n equals 1, 2, 3, 4, 5. So for n equals 5, we have 827 grams. So that is for the thick wire, thick string I should say. All right, you have the data for the thick string, mass of 0.000175, and I've started with 50, 60, 62, 64, let's try 65, 67 is too much. All right, 65 grams. So n equals 1, 2, 3, 4, 5, 6. So for n equals 6, again, this is for this is for a thin wire. I get 65 grams. Okay, I'm now going to do n equals 5. Again, you should have your table calculated. So I'll start with 50, add 20 to 70, add another 20 to make 90, getting kind of close, and 92, oh, I think we have it. All right, 94 grams. So I got 1, 2, 3, 4, 5. So for n equals 5, $94 grams is the hanging mass that makes the tension. All right, I'm next going to go to n equals 4. So I have 50, so I have 100. I had 20, 120. 140, okay, 147. So for n equals 1, 2, 1, 2, 3, 4, I get that many nodes. Okay? So that would be okay, I get 145 grams. Okay, next I'll do n equals 3. Add 100, gives me 100, 200, 250, close it looks like, 255, 257, 259. So my n equals 1, 2, 3. So maybe you can see these with the paper behind them. Maybe not. That's part of the problem when we're doing a lab by video. Okay, so there's 1, 2, 3 antinodes. It's working very nicely. All right, last one we'll do is for n equals 2. Oh, so that's, sorry. So n equals 3. $259 grams. And then we'll do the final one. N equals 2. Take off this weight. So that's 200. So let's go back. So that's 550. Okay. 570. Oh, pretty close. $575. Believe we have it. $577. So we have an so for n equals 2, we have a node, antinode here, a node in the middle, and an antinode here. So this is 500 and 79 grams. So for N equals 2, and unfortunately, do N equals 1, which would be just 1 going up and down, I'd have to put about, my estimation, about 3 or 4 kilograms on here, and I'm pretty certain I'd break the string. So that's the lab. You're going to have your original numbers. Again, for the table 1 with the thick string, I'll do one calculation for you on how to get the percent error. So we did the results for each of the different modes for thick string, thin string. I'm going to do the example I did earlier on how to calculate that. So the calculated value, again, this is thick string, is calculated was 323 grams. The experimental, it was 322 grams, as I showed you. Then the percent error, or percent difference, probably be a better word, is difference calculated minus experimental divided by calculated times 100. So that would be 323 minus 322 over 323, which would be 1 over 323 times 100, which is roughly 0.3%. So we're very close to that. Most of them should be relatively close to that. All right, so I gave you the experimental thing. The calculated ones, the percent errors are going to be based on the calculated ones using the formula I gave you in the first part of the lab video. And you can do that for data table 1, and then do the same thing for data table 2, and then for the thin string, and then get your percent. So the results are fairly close to what I would have predicted theoretically. Okay, so that's lab 11, and again, it's part of chapter 11.